Training a massive language model requires spending millions of dollars to calculate delicate, interdependent multiplicative relationships across billions of parameters. But the moment you deploy that model on standard hardware, you apply a quantization step that shatters those precise relationships. Standard 8-bit floating-point quantization treats learned weights as a flat array of isolated numbers. To save space, it takes high-precision values and rounds them to the nearest available low-precision bucket. When the rigid grid snaps into place, nodes jump to the nearest intersection. The structural links bend, warp, or sever. Post-training calibration attempts to repair this damage. Frameworks like GPTQ run thousands of samples through the broken model, guessing scale factors to patch severed nodes. This calibration is an engineering band-aid. It compensates for the initial error of treating structural, algebraic weights as disconnected floats. This inefficiency scales disastrously at the key value cache. At context lengths of 32,000 tokens or more, a single decoder's KV cache dominates the memory budget of any target device, consuming upwards of 34 gigabytes. To fit that cache onto physical hardware, engineers often rely on lossy compromises, dropping data through token eviction or blurring it through low-rank approximations. We are investigating whether memory compression and precision reduction can function without these lossy heuristics. Mapping the transformer architecture onto a specific geometric reality transforms quantization into a structure-preserving algebraic operation. The Shannon prime framework rebuilds the forward pass of a transformer as a discrete dynamical system. It places every layer operation onto a single complex multiplication elliptic curve over the imaginary quadratic field Q root -163. Components like RMS norm, attention, and QTV projections are unified as endomorphisms, transformations that map the curve to itself. The choice of -163 is precise. It is the largest Heegner number, giving this field a class number of exactly 1. This property makes its ring of integers a unique factorization domain. Because this is a unique factorization domain, every token index in the embedding table has an unambiguous prime factorization. We can store vectors only at square-free indices, those with no repeated prime factors, and use the Mobius function to reconstruct the remaining 60% of the table. This reconstruction is bit-exact in the ring of integers. Storing only square-free indices reduces the memory footprint of the KV cache by roughly 40%, without discarding any trained data. The UFD structure ensures that this KV compression results in a mathematically exact reconstruction of the original model weights. The Hasse-Weil equation dictates the mathematical limits of this algebraic engine. This formula calculates the maximum number of distinct hidden states reachable per layer. At standard prime word sizes, this ceiling hits at 31 bits per coordinate, matching the empirical capacity ceilings seen in LLM weights. Any state outside this specific orbit is unreachable from any input. The Hasse-Weil bound represents the literal Shannon limit for the model. We can now address the problem of reducing precision to FP8 while maintaining the multiplicative relationships learned during training. On a CM curve, exact quantization is performed by the Frobenius endomorphism, represented by phi-p. Because the Frobenius endomorphism lives inside the endomorphism ring, it commutes with every layer operation. It passes through the model's structural links without altering them. Reducing the model to FP8 or FP4 becomes an application of the iterated Frobenius polynomial. Since the Frobenius operation commutes, the core structural links remain fully intact, and post-training calibration data is no longer required. Analyzing prime numbers through the CM-SATO-TAT distribution allows for even higher efficiency. Under this distribution, primes partition into two distinct types, the inert primes and split primes. An inert prime like p equals 2 deterministically yields a trace of 0. This creates an encoded channel with 0 structural drift. A split prime like p equals 41 yields a small analytically bounded drift. These can be combined into an FP10 tensor, a 2-bit inert channel providing a drift-free foundation, and an 8-bit split channel managing the remaining precision. This asymmetric prime selection creates a new mixed precision format that completely eliminates variance without the need for any calibration. Remarkably, instead of requiring massive server farms, these exact algebraic structures execute natively on standard mobile processors today. On a Mistral 7B model, this framework achieves a 6.2 times reduction in KV cache memory, with zero change in measured perplexity. And a Qwen 2.5 coder model achieved 43.72 tokens per second on a mobile Snapdragon CPU, which is 3.58 times the speed of the standard baseline. Applying the UFD framework results in hardware throughput gains without trading off any model accuracy. A definitive experiment on the Phi 3 reference model is now being used to test this calibration-free approach against industry standards. While GPTQ and AWQ require thousands of data samples to calibrate for rounding errors, the Shannon prime configurations operate without any calibration samples. To validate the framework, the Shannon prime models must match the accuracy of the baseline FP16 model as closely as the calibrated methods do. Aligning inference engines with the geometric reality of elliptic curves allows for precision reduction that respects the internal symmetries of the model.